Okay, everyone. This is it. This is our last subject, kinetics. Remember, at the first class I told you, we're going to end on kinetics because that's going to be like the easiest part, and I want to end on the easiest part. Well, today's the day. I also think that this will be a bit more relevant to you. I'm going to try to inject a little more biological examples, even today. And we can relate this to like the spread of disease and whatnot, the progression of illness, and so I think you'll like this part. And plus, mathematically this is all not double derivatives like the kinetic energy operator of the Schrödinger equation. These are all way easier. They're all differential equations, but they're not second order differential equations. They're first order differential equations, and these you can solve. You actually probably learned how to solve them in Calc 1, even though they may not have explicitly called them differential equations. You can solve these, that's my point. All right, now, as with every class, I try to review, and in terms of strategy, I hope you realize that whenever I review for the purposes of reviewing. I found it very useful when I was your age, because I found from class to class, I was like, oh yeah, I could totally forget what we talked about 2 days ago. But notice that, like, what happens is right before I'm setting up the camera and whatnot, I'm just thinking myself, oh, what did I talk about last time? Well, I'm going to bring up what comes to mind. So what do you think happens when I write the test, right? Now, I told you the ability to strategize and think about, like, observe me and figure out, like, what am I giving you hints and cheat codes. That's really smart of you, and I appreciate it. So with that said, here's what came to mind about last lecture, which I know was a little bit rough. We had an easy patch of spectroscopy and the electromagnetic spectrum. Remember that, so there weren't tons of equations, but there was just like a lot of stuff, and so that offers the opportunity for a lot of shorter answer questions, which the tests are mostly composed of. So think about that. The last lecture was a little bit more difficult because of that Frank Condon thing, but let me give a bigger picture, which I can do in review. I have a little bit of a hard time talking about big pictures when I'm going over the details in the lecture, but on the next day review, I can kind of step back a bit. So we started out talking about, and to summarize the last two lectures, rotation and vibration, and it was kind of interesting that rotational spectra, you can see that only in the gas phase, and we talked about why you can't see it in the liquid phase. So if you're doing gas phase, you can see rotational spectra, and you can also see the rotational structure on top of the vibrational structure. And you've covered that extensively in PChem lab. And we talked about why last time. So you can see these individual rotational transitions on top of the vibrational one. We also talked a little bit about normal modes, so don't forget that. And there's also nothing lower than rotation, right? Energy scale, there's nothing lower than rotation. Then we have vibration, and then we have electronic transitions, and then core electronic transitions at the top for X-ray and gamma ray and stuff. Okay, when it comes to absorption, which we generally do, absorption spectroscopy, UV spectroscopy are generally done in liquid and solid phase. So I don't really know of too many people doing absorption spectroscopy in the gas phase. So you're not going to see rotational fingerprints, but you can see vibrational fingerprints. And that was the Frank Condon principle. And so that's where we've gotten some equations. And I know it was just a whole bunch of details and a bunch of subscripts. So I'm just writing it down again. A bunch of subscripts, a bunch of psi stars and all that. It was a bit much, I know, but this one's kind of important. It's one of the key concept in PChem. And I brought up the concept of, I brought up pyrene, so you see an electronic transition, but you see these vibrational progressions built on top of the absorption, electronic transition, just the same way you saw rotation built on top of the vibration for something like HCl or whatever molecule you're studying in PChem lab. And recall that comes about because the dipole operator is minus E for units. That just gives you units. And normally we would think of that as where the electron for a hydrogen atom is just the distance between the proton and the electron, because that's all that the atom has. But when it comes to a molecule, we have to now take into account there can be multiple electrons, and you can have multiple nuclei. So that was, so I need to put the minus E on the outside, sorry. I didn't think about this ahead of time. Okay, so we have we have electrons, and we also have nuclei. And when you now use that for the difference dipole operator, you end up with a term that is for electronic transitions. Now, as I mentioned, this is exactly the same thing for the hydrogen atom, and you're doing that, or you've turned it in yet. Actually, I'm kind of confused with it. So anyway, you know on your homework that you had to do a whole bunch of different dipole calculations for a whole bunch of different problems. So hopefully, yeah, hopefully I hope you have a handle on this now. And of course, the dipole operator ends up taking on the polarization of the light itself. For a molecule, you pick up this extra term, which is the Frank-Condon part, which is that you have the vibration in one electronic state integrated against the vibrational wave function in, well, a ground state, assuming that we're always in the ground state, which is a reasonable assumption. And those end up looking something like this. So here's wave function final state, here's a wave function in the initial state. So notice I'm drawing two wave functions, and they can be displaced. So here's the ground state and the excited state, ground state, vibration, and it doesn't look like there's a lot of overlap, but then the excited state, maybe the second state, vibrational state looks like that, and look at that, now there's tons of overlap. Okay, and so that's why you see different vibrational transitions, and they have different strengths, because it depends on how these overlap. Okay, anyway, I've rattled on way too long about this. As I mentioned, we are on a completely different subject, kinetics. I promise this is going to be way easier. And what about it? And I've lost my notes. Okay. All right. So this is all about reactions. And a reaction could include a person giving COVID to another person. That actually would be legit. And it certainly would be similar to any chemical reaction I could come up with. Now, what I'm writing up here, I'm going to do this a lot. I'm just going to say A reacts with B, and it gives C and D, just because, I can look through the chemical literature, I don't know, hundreds of millions of papers and find examples that fit this stoichiometry. So I'm just not even saying what it is, because it just doesn't matter. I'm trying to choose something a little bit more kind of complicated, even and odd, multiple reactants, multiple products, because, I mentioned this a couple times. What I really hate is when you get a very simple example, A goes to B, and you see how to work all the problems. And then you get A plus B goes to C, and you realize that none of those equations work, like not even the beginning equation. You don't even know how to set it up. So I like to start with kind of a complicated example. So anything else I throw at you would be as hard or simpler than this. So that's why I tend to do that. I'm going to vary the type of reaction I'm describing continuously, so be careful of that. Now, the reason I'm writing a more complicated one is because kinetics is all about rates of reaction. I mean, if you were to go up to someone on the street, and they probably know the word kinetics, and if you said, what's kinetics of a reaction, they would probably just naturally say, well, it has to do with the rate. So anyone on the street would probably know that, and that's true. So what is the rate of a reaction? Okay, well, that would be how fast it goes, right? Again, what would a person on the street say? Well, they'd say it's as fast as it goes. They'd say that about a car too, right? Now, what does that mean? And remember, we're in mathematical land. Well, now, the one thing I'll throw at you is think concentrations, right? Because what else would you describe, right? So it would be the rate of change, and again, let's choose concentrations. And I'll just pick on A. Now, A is a reactant, so that sounds like a good thing to pick on to begin with. Now, we like to express a lot of kinetic relationships as we're going to, I'm going to put bunch of equations on the board. In honesty, you know it's coming. So we're kind of back to equation land. But whenever we do all the kinetic analyses you're going to see, we generally like to express them with regard to reagents. Now the reason is, it's because that's the one thing you always can control. Now technically, I'm going to scoop in 1 mole of A and 3 moles of B. Now the laws of physics and nature and chemical kinetics and thermodynamics dictate how much products I get, right? I don't really control that. I control what I was able to scoop in, but once I've done that, then I'm no longer in control. So to some degree, you could also cast kinetics in the form of products too, because again, it shouldn't matter. Once it's set up, it's going to go. So I could define the rate in terms of products forming as well, and I will do that. However, if you have a choice, we always analyze and think about kinetics as reactants. Again, for the reason that that is the thing that you can scoop in. You always can control that, and then nothing more. Okay, next thing. This is negative. The rate is negative, right? Because reactants can only go away. Now, here's the thing. People were studying this back in 1800. And I'm not joking when I say I think the reason that they define a rate as the negative change of a reactant with time is because they didn't want to publish, when they published rates, like in journals, they didn't want to lose ink on the minus sign. Seriously, I think that's why they did that. So again, we like to talk about the rate of change of reactants over time, but it's naturally negative because reactants concentrations are going to drop. So the change in A will be negative, the change in T can only be positive, time only goes forward. And so they put a minus sign so that when they publish papers, they could write a positive rate constant, didn't have to blow ink on minus signs. Okay, now it turns out that for whatever reason, B is a reactant too. So I would like to express that as the change in B as well. And it'll be negative, but let me point out. Let's say in 1 minute, 1 mole of A reacts. So the rate is minus 1 mole over 1 minute, minus 1 over 1, so that's plus 1 mole per minute. Now if you do the same for B, if 1 mole of A reacts in a minute, minus 1 change, then the change in B is minus 3 moles, right? So you're going to want to put a minus, again, minus for all the reasons I just said, minus 1/3. Now that's called the stoichiometric coefficient. So you put 1 over the stoichiometric coefficient. So again, you see why I like to throw kind of complicated examples at you at first, so that, if I just show you A goes to B, and then I show you this, and I'm like, well, what is it with respect to B? And you're like, you don't know what to do with the 3, right? Anyway, that's why I do that. Now, as I mentioned, you can write this in terms of the products, and the differences, of course, is, 1 over the stoichiometric coefficient. You don't need a negative sign because the concentration of C will increase. Remember, it starts at 0, so it can only go up in time. And then we don't have the stoichiometric coefficient of D is 1. So there you go. And we give this a little right there. That's what we call the rate. So I pretty much always see that. Notice as well, we can ascribe units. Molarity, I had to look at it for a second. Molarity per second, so there you go. That's going to be important a little bit later on, so just look out for that. Okay, so problem. Let's say we have 1.1 moles of A, 1.1. Now in minute 1 I said 1 mole reacts away. So in the first minute I had minus 1 mole in 1 minute, so I have a 1 molarity per minute reacting away, oh, for 60 seconds, sorry. Okay, what about the next minute? Well, there's only 0.1 moles per liter left, right? So if I had 1.1 moles per liter and 1 moles per liter reacted in the first minute, then there's only 0.1 in the next minute. So that means that the rate is changing with time, right? Because if you have if a high concentration of A you have at the beginning because you have a lot of A, and it reacts quickly, you're just going to have a bigger number of moles per liter will react initially. And later, there's just less. You have less of a change because you just don't have as much to begin with in that later time period. That means that the rate is time dependent. That sucks, right? Think about that. How am I supposed to write a journal article and describe a rate of reaction when it matters when I measured it? We'll measure it always at the beginning. Okay, good thinking, but what if that's not practical? Right? What if something goes boom, right? Like hydrogen and oxygen, it goes so quickly, maybe I can't measure that. So I can think of all kinds of problems, right? Okay, so now we run into our first issue that I certainly, this has all been logical, right? It makes sense that we would measure kinetics by rate because those are like the same thing. And it makes sense what I describe as a rate. But now I'm telling you I can't really publish that because I'm not even sure how to measure it because it's always changing. Okay, it turns out we can, but that's basically the subject of the next 4 lectures, is how do I express information that is usable to all people in light of the fact that the rate by itself is changing. So I'm going to have to express this rate in ways that is transferable. Okay, now that means that there are 2 things that are the most important about kinetics. One is called the kinetic order. Now the kinetic order, I'll explain in a minute, but well, here I can kind of, let me go ahead and jump ahead a little bit. So here's an example. What you're going to see is that I can express the rate as some kind of rate constant, which we universally call K, concentration to a power. Okay, so this power is what we call the order. Okay, so there you go. So now you're seeing, what you're seeing is that the rate is proportional to a concentration to a power. So the power is the order. Now, right now, I'm going to get more into what this means, what this kinetic order, what this coefficient, the first power, what does that mean? We're going to spend a long time on that. Right now, just for your note taking, just note that the kinetic order is when you write the rate as proportional to concentration to a power, that power is the order of the reaction. Order of the reaction kinetics. Okay, I'll go ahead and tell you a little bit about why it's important, because it tells you quite a bit about how the reaction occurs. Again, we're going to be spending tons of time on that. All right, next thing, and I've also just shown this, kinetic rate constants. And that is right there. That's the rate constant. So there you go. Basically, what we call this, we call this a rate law. The rate is equal to a rate constant, concentration to a power. So this guy is terribly, terribly important. Now, you can imagine that the rate constants, those are what get published in journals. That is the best way I have to express to you what to expect if you want to use this reaction, and it's important to you to know how fast it goes because you have a chemical plant, and it's terribly important to know how fast your products are made. Let's say that the rate is very high. Well, that means that the reaction could get out of control. Let's say it's exothermic with a high rate of rate constant. Well, that could explode, right? So that's what an explosion is. When a reaction occurs so quickly and builds up so much heat that usually, let's say you're doing a liquid reaction, it vaporizes. Now that is an explosion. So knowing a rate constant would be pretty crucial for that. You definitely want to know that, right? And you can figure out whether enough heat will be evolved to cause an explosion or not. If you're not competent enough to do that, you wouldn't be in charge of designing a chemical plant, would you? Okay, and again, the rate order tells you about mechanism, and that's what we're going to spend quite a bit of time on. Okay, next bit for a rate constant, note that if the rate is molarity per second, and of course concentration is of course in molarity, then the units of the rate constant are 1/seconds. Technically hertz, right? Okay. Now, as you'll see, it would depend on the rate order. So, ooh, that doesn't look good. That bothers me. There we go. So, rate constants have units of 1/second, depending on the rate order. So notice that if this, let's say that this was a squared, and I'll show you why that would be in a minute, but let's say it was a squared. So this would be molarity per second. If the power is 2, this would be molarity squared. And so the rate constant would be 1/moles, 1/seconds. Molarity, 1/molarity, 1/second. That would be the rate constant. So the rate constant is going to depend on this, on the kinetic order. And that would be something I could probably throw in a short answer question. I can kind of, based on how a reaction occurs, I can write different equations for the rate, and then I could ask you what the units are. So that'd be a really simple, easy question that hopefully you would rack up points. Okay, so what I want to do is now make use of why is it that this little expression here, why is this useful? Why does this transfer information such that, you know, if I publish this information, why is it that someone else has all the information they could ever use to reproduce it and again know whether they're building a safe chemical plant, which would be one of the most important things that chemists could do. Let's see now. The first thing I'd want to do is, how do you know what a rate order is? And the way to do that, let's see here. Here's this little rate expression. So now I'm going to write this to some order. Now what I would do is I would take a log of it. So what you'd have to do is you'd have to do an experiment. You'd have to have some way of measuring rates. And what you would do is you'd vary the concentration. And then what you do is you'd have a table of rates and a table of concentrations. And you could plot a line, but not of the rate versus concentration, but of the log of the rate. And if I took the log of all this, let's see, now, if I ask you something like this on an exam, hopefully you're looking at the cheat sheet. Because what you want to do is look for properties of logarithms. Log of A times B is going to be log of A, where A is K, plus log of this other thing. Now, yeah, let me write that down. Okay, next one. I'm not even going to write down the next thing because what I need to know is another identity. So B to the N. Here's another property of logarithms. And this could be a base 10 log. That's the normal log. It could be the ln, right? That's the exponential type log. It wouldn't matter. The properties are actually the same. Okay, so what would I get? I would get order times log concentration. Okay, so therefore, what you would do is plot. Again, you'd have to do a fair number of experiments, at least 3, because 2 points will always be fittable by a line. So if you want to know that if the relationship is linear between a rate and the log of the concentration, you're going to have at least 3 points. Okay, so what you would get is a line like that. And the slope, so there's the intercept, so you notice how I drew a positive intercept, and the slope is the order of the reaction. Okay, so again, it's pretty easy to figure this out. Okay, now the next thing is, as I mentioned, order and rate constant are the things I give people to transfer the information about this reaction. This transfers all the information you need to know about the reaction, not the rate itself, which depends on concentration, so therefore it depends on how you set it up. That's not very useful. That's not useful because you can't count on people doing everything the exact same way. You know, someone setting up a chemical plant may be making this thing 1,000,000 times bigger with as much concentration as they can to drive, to get as much products as possible. And if they're going to vary conditions, they don't know what's going to happen, right? I report to you what happened with my rate under my conditions, but you don't know what's going to happen under your conditions. That's not useful. So of course, what I'm expressing is the rate of the order. Okay, so why is that useful? Okay, let me summarize that again, because again, this is horribly important. Don't forget what I first defined the rate as, and in my publication, I tell you, oh, this is a first order reaction. And so you know to write the rate constant, and I gave you the rate constant. And I told you it's a first order reaction, and so you put a 8 to the first power, meaning just concentration of A. Right? You would know to do that. Okay, these are the same thing, so let's put them together. Minus the change in A is equal to K times the concentration of A. All right? Now, what you've got, now I bet you've seen this even in first semester calc. I guess, I don't really know, I wasn't there. But this is a diffie-cube. Like, this is a differential equation. It's just like the Schrodinger equation, except that it's a first order differential equation. And in fact, I hope you look at this and say, oh, that's not going to be nearly as hard as the Schrodinger equation. Correct. It is not as hard as the Schrodinger equation. This is unbelievably easy compared to the Schrodinger equation. So, you can imagine, though, I always struggle with this. Should I begin with the class with this and then beat you over the head with all the Schrodinger equation, or should I do Schrodinger equation then this? Well, you tell me, but here we are. So you don't have a choice. How do you solve this? Unbelievably easy. Let's bring the dt over here and the change in A over to the right. So dt to the right, concentration of A to the left. Okay, so now the reason to do that is that kind of like separability. You do remember separability, right? You want like terms together. All right, so I've got a change in A, and there's not much I can do with this. So I want the concentration, the change in concentration of A. So I want the concentration of A on the left. I'll bring over that minus sign as well. And so I'll take everything else, including that minus sign, and bring it over to the right. Okay, next bit, just integrate it. So, let's see what you do here. Just integrate. So I'm going to have partials, right? I have partials. Something I try to very dramatically emphasize this in PChem 1, and again, I wasn't there, I don't know, is that I think that you run into something just like this in the Gibbs-Helmholtz equation. Remember that? The Gibbs-Helmholtz equation is one of the times you run into something very similar to this. The most important thing is when you've got partial on the left, partial on the right, partial on the left, partial on the right, and you're going to integrate them. the limits of the integrals have to make sense. They have to work together. For example, we're going to start the integral. So the limits are also the same thing as the partial, right? I bet you haven't thought about that, but they are. Meaning that I'm integrating dt, that's time. That means the limits are in units of time. I will start at t equals 0 because why wouldn't I? Now here's a clever trick. I don't know if you've noticed this before, but this is done more frequently than people realize. I'll integrate up to, say, sometime later. I'll call that capital T. But you know what's often done, and I tend to do this, so I might as well go ahead and do it now. You can just integrate to just regular T. Okay. So you can just integrate to regular T. And I technically shouldn't do this, right? Because I'm integrating with respect to little t, so I can't have the upper limit, I can't have the same thing, right? You can't be integrating and have the integrand in the limit. Really what's happening is that this is a different t. So it's often not expressed in scientific derivations that this upper limit and this t are not the same thing. If you really have a good text, then what they'll do is they'll use like a capital T, or what they'll be, if they're really, really good about being careful about this, they'll use a T dash to make sure that you understand those are not the same T. But you know what? Most of the time, you just don't see it done. I just want to point that out. So let me do the left side. If this is T equals 0, then the lower limit would be the concentration at T equals 0. So if this is T equals 0, this is the concentration of A at T equals 0. How do I know it's the concentration of A? Because it's the partial of the concentration of A. Therefore, the limits are concentrations of A. At time 0 on the lower one, because the lower limit on the other side is T0. Okay, now just like I was babbling on about how, this is a big T or a little t, what you have on the upper limit on the other side is A at that time, the future concentration of A. Okay, now let's integrate this. This is the this is kind of crowded, isn't it? This is the integral of 1 over x. The integral of 1 over x, if you're at an exam, you should know not to sit there and say, oh wait, is that 1 over x squared minus 1 over x squared? It's minus 1 over, no, it's natural log. But before you start doing those mental gymnastics, what do? You hopefully are shouting at those of you who are going to get A's are going to say, I should be looking at the cheat sheet, right? Now remember, I told you on the last exam that one of the things I could see that you were doing wrong is you're not looking at the cheat sheet. You look at the cheat sheet when you know you have an equation that you need to solve, but you need to look at the cheat sheet at other times. There's still answers there, even for questions you don't think you need the cheat sheet for. So if you're stuck on a question, look at the cheat sheet even if you don't think you need it. Anyway, you're seeing the integral of 1 over x. Look at the cheat sheet, the answer is natural log. Okay, so you end up with natural log, and I'm going to go ahead and do 2 steps at once. Natural log of the upper limit minus the natural log of the lower limit. Hopefully you know enough about natural logs to know that's the natural log of the top minus the bottom. There you go. Lots of brackets. Okay, there you go. Okay, well, let's do the other side. Actually, let me do it up here. And then I'll bring it down here in a second. Okay, so nothing is more easy to integrate than just dx or dt. It's minus kt from 0 to t. And again, you can see how it's improper to have the same, lowercase t. Regardless, what you get, minus plus, there you go. So again, this is so simple, I just did it, right? Okay, minus kt. Next bit, I'm just going to assume that you can do this just fine. Take e to the both sides. You know, e to the natural log of x is x. So I'm going to just take it for granted that you now know that I'm looking at the concentration over time. And that means I bring the concentration of A, the initial, at time equals 0, over to the right, and have e to the minus kt. There you go. And that's a single exponential decay. Yeah, so with this information, you know. So I published a paper, and I said the rate order is first power, and the rate constant is 10 to the 9 per second. Now, anyone competent should know that the way that this thing changes over time will be whatever they decided. You see why it's important? They can decide what they want their concentration to be. That's up to them. And again, anyone who's in charge of like a chemical factory is not a moron. So they put in a number that is good for them, that won't blow up. They know the rate, and of course time is time, so now they know exactly what's going to happen, right? So I didn't publish a bunch of rates at time 0 and then a minute later and a minute later for whatever concentration I ran at. I did make those measurements, but what I published is first order, there's a little 1 there, and the rate constant, and that imparts the ability to know what's going to happen. And again, one of the things that someone competent would want to know is, given how quick this reaction is and how exothermic it is, you would want to calculate, like, okay, how much heat is given off, what's the enthalpy of the solvent, and if you find that there's enough heat given off to vaporize the solvent, it is going to explode, right? So that's, again, why we need to do these types of things, to keep people from blowing up. Okay, now here's another thing to be conscientious of, is that this is often expressed, oh, I'm in a corner. This is often expressed this way, T over tau. So rate constants, Ks, are often expressed, rate constants, first order rate constants are per second. So sometimes what you do is people write e to the minus t over tau, where tau is 1 over the rate, and tau has the units of seconds. It's just a little bit more appealing. So when you tell me a rate is 10 to the minus 9, 10 to the 9, I'm like, okay. All right, but now 1 over that is 10 to the minus 9, and what, so that's a nanosecond, right? That's a nanosecond. So you're telling me that this thing reacts in a nanosecond, right? Tau is a nanosecond. Now that's fast. I know, I know a nanosecond is fast. That's a very fast reaction. That's one you should be afraid of, right? Fast reactions can go crazy. So that's why, so you see how you tell me the rate is 10 to the minus 9, 10 to the 9, that's a big number, but I'm not quite sure how to interpret it. Instead you tell me, well, tau, the lifetime is a nanosecond, and I can immediately comprehend that that is very fast. So that's one reason that's done. People tend to switch back and forth between K and tau. In what, like I read papers for a living, and I will see in a single paper a rate turn into a lifetime, a tau's lifetime. I've seen papers switch back and forth between those representations, which is kind of dumb. I mean, I know what they're doing, but that's kind of dumb. That's sloppy. Okay, I see I've got about 10 minutes left. I'm going to go over, let's see, I actually don't know what I'm going to go over. I'm just going to go over some more stuff. I have to wipe out the board, and then we're just going to talk about more stuff. All right. Okay, now, here's a good question. Let me point out something I did to you there. In that previous mathematical derivation, I wrote this down, right? This little rate expression, this little rate law. And then I set that equal to the derivative, and we did some mathematics, and you felt good about it because it wasn't hard. But who says, where does this come from? Who says this is true, right? That's a presumption. I just gave it to you, and because I just kept rolling, you just accepted it. You got to look out for that kind of thing. That's something people use to manipulate you. They'll often show something that's maybe a proposition, a hypothesis, But then they just keep going from there and never allow you the critical time to think about, was this correct to begin with? Well, now it is. I'm not just making everything up. The reason that this rate expression is valid, it's a valid starting point, is because we can think of rate as a manifestation of probability. So what this states is that something will occur faster if the agent responsible for that action, that something, is present in greater abundance. Once again, if something is going to do something, like A will react to form a product, a person will go crazy, it will occur faster if more of those things are present. So if we have just one A molecule that's going to react, you might be waiting a long time before it chooses to do so. But if you have a whole bunch of them, you know that one of them is going to go off on its own sooner than the others. The more of them that are present, the more likely one of them will choose to go off sooner than the others. Therefore, the rate is proportional to the number of things that are responsible for the dynamic of which we are measuring said rate. So rates in kinetics are really a statement of probability. And again, the probability is proportional. It's more probable for something to happen if the agent's responsible for that thing, if there's more of them. So that's really what all this comes down to. Now, that means that if the power is first order, so the power is 1, the reaction is this: A goes to B. Okay, I didn't tell you that yet. So now you can't have known that. Don't think, oh, I should have known that. I'm telling you that right now. First order reactions are just something turning into something else. And that's how you know that it's, when you have, like, this would be like an isomerization reaction, and that's why it is a purely exponential decay. And I can draw exponentials, I think, fairly well, so I've been doing it for many, many years. Okay, so this thing is going to go off on its own. And again, an isomerization or radioactive decay, those are good examples. Okay, now what about this? Let's get away from first order reactions, isomerizations, nuclear decay. Those are really about it. These are actually not that interesting. And let me tell you, we've actually talked everything we can talk about first order. There's nothing more to discuss. We talked about rate laws, first order. We've integrated this. It's an exponential decay. There actually is nothing else to talk about. Next thing we can talk about, however, let's think about two A's. An A has to react with an A. So this is like, this is called autocatalytic, by the way. It's when something reacts with itself. That's scary, by the way. Let's just say I have some experience with autocatalytic reactions. The scariest thing imaginable is A reacts with A to form B. Okay, so that is, guess what? So that would be a second order reaction. So the probability that that reaction occurs is now going to be proportional to A squared. Now that's because an A has to find another A. And so the probability now multiplies. You can see that in kind of two ways. Imagine that if the molarity of the concentration is small, that's going to actually slow the reaction down, right? Because let's say like the concentration is like 0.01. Well, the probability, which is proportional to the rate of an occurrence, is now 0.01 times 0.01, right? So if you have a small concentration, the rate is going to be the square of that. And so that's actually going to slow it down. But the converse is true. If you have a high concentration, let's say the concentration is 10, those things are finding each other really, really quick. And once the two find each other, then it's probable that they react, and that means you're going to observe a faster rate. Now, so you see how all this actually makes sense, right? Okay, so second order reactions have probability proportional to the square of concentration. Okay, so what I will do is solve a second order rate relationship, and that'll be enough for today. But let me point out that like in COVID, you see how this can get out of hand? The more people that have it, it's a nonlinear increase in its spread. The more people get it, especially within an area, it's so much more likely that a body comes into contact with another person, and the spread will go as the square of the population of people infected. So that's because one person can't give it to themselves. It doesn't make sense. So spreading disease is inherently similar to a second order reaction. In a second order reaction, high concentration gets out of control. Okay, so let's solve this one. All right, now what that means is if, it's 2A goes to B is our reaction. Then the rate expression, again, I think this is called a rate law, I have to look that up, is, I've gone blind, where am I? Okay, it'll be the rate constant to the order, and again, this is a second order reaction because there's two A's reacting with each other. Okay, now we know that the rate is minus the derivative because A is our reactant. Now, like last time, we're going to separate, we're going to group like things together. Okay, it's not too hard there. And now we're going to integrate from time equals 0. And that means we're going to integrate at the initial concentration. And then again, I'll do my little trick of, what have I done? dt. Right? What I wrote there doesn't make any sense. You have to have a partial. Okay. And again, you see I've used the same letter, which is bad practice, but I'm going to do it anyway. It's often done. Okay. So, and then the upper limit is the concentration at A at some time later. Okay, let me do this part on the right because it's unbelievably easy. Now let's do this one. Okay. Now again, you know to look at the cheat sheet, but I happen to know the integral of 1 over x squared is simply 1 over x. Minus 1 over x. Because the derivative of minus 1 over x is 1 over x squared. Anyway, okay, so I can do it in my head, good for me. Okay, so what that means is that this is 1 over the concentration of A over the, it's minus, right? It's minus, so you know what? Let me bring that minus over here. Sorry, let me actually keep that minus over here. And then that minus becomes a plus. Now again, the integral of 1 over x squared is minus 1 over x. So actually, I'm going to keep that minus over here. And now I've got minus 1 over the concentration of A from A at time equals 0. A at time t. Okay, so that means I've got 1 over concentration of A at times t minus because you subtract the lower limit. And that's equal to kt. And you know what? You can actually just stop there. There you go. And you can plug in numbers, and you probably would use a computer at this point to look at how this reacts if this is your reaction. But you can do some algebra. And I'm not going to do it because again, this is not high school. You are perfectly capable of doing some algebra to solve for A of t, and maybe try that on your own, because if you can't do that, you're going to lose at that show, Am I Smarter Than a Sixth Grader? Which actually I think dates me, right? How long ago was that show on? Anyway, so here's what the thing looks like. Sorry, it doesn't look good, it bothers me. There we go. Okay, so that is what it looks like if you do some algebra there. Okay. Now, in terms of plotting it, it would look like this. Sorry, I'm not using the board too well. Versus time. What you have, basically, this is like 1 over x plus 1. That's what that looks like. Remember that I'm saying x is the x-axis, but it's really time. So let's just say the concentration was 1 over some numbers times x plus 1. And I can put that in my graphing calculator. And what I would see is behavior kind of like this. Oops, not good. That was a screw up. All right, so what it does is it hugs the axes. That's not like exponential. I'm exaggerating this a bit. Now that's second order. First order is a pure exponential, looks more like that. So I can actually, I've been doing this for years. If I look at a graph of products versus time, I can usually spot the difference between first and second order based on how it hugs the axes, or not, in which case it's first order. Okay, so folks, I'm out of time. I think I went a little over. This is just your introduction to rate laws. We get these rate expressions. Everything is a rate constant, the thing responsible for the action, the order. The order, did you notice this? The order actually has to do with the stoichiometric coefficient. I didn't mention that before, but that's going to be the subject of the next lecture. Next lecture, we're going to look at a lot more complex reactions. And again, in this case, because 2a's, the stoichiometric coefficient is 2, the little rate expression here has a squared. You set up your diffie-q, and you go from there. Now, the two that you've seen, first and second order, to be blunt, those are the easiest ones. I mean, how hard was this? It's not that hard. Unfortunately, it does get harder. And in fact, sometimes complicated enough, even though these are first order diffie-q's, first order diffie-q's can still get pretty hard. So I'm actually not going to solve any more of them. I'm just going to, just like quantum, I'm going to set up the diffie-q, and then I'm going to give the solution. So just heads up on that. All right, so anyway, I think this is enough for today. So come back next time because you have no choice. And we're going to go over much more complicated reactions and their rate expressions, and also a little bit more about why we do this to begin with. So that'll be for next time, and I will see you all then.